used for natural language processing concepts like recurrent neural network, uh, LSTM, long short-term memory network, and gated recurrent neural net, etc. So we can use those neural networks for different types of applications. So one application is one-to-one application where you can use that architecture for simple binary classification kind of task. And there is one another model which is called as one-to-many architecture. So we use such architecture for image caption task. So in one-to-many architecture, in the second image, you can see that one-to-many architecture. So that kind of architectures are used if your input is one single entity and your output is a sequence of entities, like sequence of words or characters, something like that. Okay, if you have some architectures like that, then you can use or design the or formulate the problem or application using this architecture. And there is another architecture, many to one. This can be used in applications like sentiment analysis, topic classification, any kind of classification. It can be either binary classification or multi-class classification. Okay. Only thing is your input should be a sequence of words or sequence of characters or sequence of any entities, and your output is going to be one single entity. Okay. And another important architecture is many to many. Okay, many to many. This particular architecture, the fourth image, is called as encoder-decoder architecture. The second image, one-to-many, can also be considered as encoder-decoder architecture. And in many-to-many architecture, the second many-to-many architecture, which can be used in applications like machine translation, text summarization, question answering, etc. So where we have a sequence of words or characters as input and another sequence of characters or words as output. So these two architectures are called as encoder-decoder architecture. And one more many-to-many architecture is there, which can be used to implement POS tagging, part of speech tagging applications, and named entity recognition tasks. Okay? Those kind of natural language processing tasks where the inputs and outputs are connected together. Inputs means, I'll give you one simple example. In part of speech tagging, the words are connected and the labels are also connected, or the outputs are also connected, because if you want to predict, suppose the part of speech of one word is adjective, the part of speech of next word should be a noun. It cannot be an adverb or verb or something like that. Okay, it has to be a noun. So how do you get that information? How do the machine learn that information? By looking into the previous predictions and the relationship between the words only. Okay, so in that case, or in such cases, we can use the many-to-many applications. Okay, or the last many-to-many architecture. So in our session, we are going to focus on one-to-many and many-to-many, two different encoder-decoder architecture, which can be, and I'll be taking examples of image captioning and machine translation as examples, and I'll show you how to implement the encoder-decoder architecture by using attention mechanism. At the end of this session, we will see how the attention mechanism can be implemented, and we will see the mathematical representation for the attention mechanism. Okay, so this is the image captioning problem. Uh, in this problem, the problem definition is like, given an image, you have to generate a sequence of words or something which describes that image. So this is a very important task in many applications. So this example is, it may looks very simple, but it has a lot of potential in biomedical applications. For example, if you show the, or if you feed your X-ray image or MRI, any scanned image to the model, then you will get some summary of or report of the image. Okay, you can apply that concept in biomedical domain, and you can find such similar applications in other domains as well. Okay, so this is the problem. So our objective is to generate a sequence of text for a given image. So how do we do that? Okay, that is the question we have, and this is the model I am going to use for designing this problem. So the input is one single image, and the output is going to be a sequence of words which describes the input image. Okay, so here we have to predict the words Sachin is hitting the ball with his bat, and you should also mark the end of the sentence with the help of some full stop or question mark or exclamation mark or some marker like end. Okay, in this example you can find one marker called end. Okay, so in this way you can you have to mark the end of the sentence also. So how this algorithm works actually, or how this architecture is designed. So what you have to do is, as we all know, the computers can deal only with the numbers. Okay, it can process the text, or it can, you have to convert the image into some pixel values, and you have to convert text into some vectorial representation using word embedding algorithm. You had heard about different word embedding algorithms in the yesterday session, right? So that is our objective. Okay, so given an image, you have to convert the image into some vectorial representation using any neural network. So basically in image processing, we rely on algorithms like either using a deep neural network or convolutional neural network. Using any of the convolutional neural network architectures, okay, we can convert the image into one vectorial representation, and we assume that that vector representation contains the entire meaning or the information related to that particular input image. Okay, so based on that vector which represents the essence of the input image, the algorithm, okay, starts generating the words like Sachin is hitting the ball with his bat. Okay, so to generate that thing, we have to use a concept called language modeling. A language modeling is a natural language processing concepts. Okay, there are two definitions for language modeling. So one definition is the language model is basically used for predicting the sequence of predicting the probability of a sequence of words, or predicting the next word given a sequence of words. So you can see that application in Google search or other search engines. When you type a few keywords, Google search engine will predict the next few characters or words and list out a list of predicted sentences. Okay, it is an implementation of language modeling. So here we are using the language modeling concept. So based on the vector representation of the image, we start generate, or the model generates the word Sachin. Based on the word Sachin, it start generating the word is. Based on Sachin and is, it will generate hitting. So based on the previous three words, it will generate the next word the. Okay, so we capture the contextual information, or the relationship between the words in the sentences to predict the next word. So that is the reason that concept is actually called as language modeling. Okay, given a sequence of word, what is the probability of getting the next word? What is the probability of getting hitting if the previous words are such an is and the contextual vector, or the vector representing the image? Okay, what is the probability of getting the word ball given the previous word such is getting the, okay, and the vector which represents the image? Okay, so that is actually language modeling concept. And if you want to capture the contextual relationship between the words, you have to use algorithms like recurrent neural network, or long short-term memory network, or gated recurrent unit. Hope you know the difference between these three algorithms. Okay, recurrent neural network has a lot of limitations like vanishing gradient problem, and it won't be able to capture very long dependencies in the data. So to reduce that problem, only long short-term memory networks were proposed. Long short-term memory networks can capture lengthy contextual relationship, as well as the short contextual relationship. But the problem is LSTM has a lot of parameters to be trained. So that is the reason why gated recurrent unit was proposed. Okay, it is similar to LSTM, but uses less number of parameters. So you can use any of these networks to design the decoder part. Decoder part means the architecture which is used for generating the words in English or in any other language. Okay, so that part is called as decoder, and the other part, which is called as encoder, is used for generating the vector representation for the input image. Okay, so finally you can have something like this. Okay, we feed the input image into a CNN network, convolutional neural network. So the output of the convolutional neural network is going to be a vector. Okay, so FC represents fully connected layer. Okay, at the end of, basically in neural network, the layer which just before the output layer is going to be a fully connected layer. Okay, which represents the, or which gives you the better feature representation of the input data. So FC is going to be the fully connected network, and you can have one, it can be converted into another vector called S0. Okay, then uh, that S0 should be considered as the previous hidden layer information of the first time step in the recurrent neural network we use in the decoder side. So recurrent neural network uses previous hidden layer information for capturing the previous contextual information, right? So in the first time step, we don't have in recurrent neural network, we basically initializes the previous information as 0 vector, because for the first time step we don't have any previous information. But in this case, in this example, or in the encoder-decoder architecture, we consider the vectorial representation of the image as the previous hidden layer information of the input image. Sorry, previous layer information of the decoder network. Okay, so you can do that in multiple ways. The only thing you have to consider is the size of the dimension of h0 and s0 has to be the same. Okay, so if you want, you can convert fc into a vector s0, or you can directly say that the size, you can directly mention while implementing the neural network by putting the size of fc similar to the size of h0. Okay, so you can directly connect, or you can directly use the output of fc as the previous header information of h0. So here what we do, we feed the start symbol and the previous hidden layer information to the, or which is the encoder net, representation of the input image to the neural network. Okay, or our recurrent neural network. It will compute h1 hidden layer information for the first time step, and it will predict the word Sachin, and given the word Sachin, and it will start predicting is. Okay, so given the word is, so here h2 is computed using Sachin, and h1 information, whh and h1 is used here, right? So h2 is computed using h1 and this word. Okay, so it means that h1 is actually computed using start. So h2 is computed using h1 and Sachin. So it means that h2 is computed using the the first word and the start symbol of the sentence. Okay. Then in the case of hitting, it is using, you can see the dotted line is. Okay. So h2 and is are used for generating the word hitting. So is actually computed using the word Sachin. Okay. The word Sachin is computed using start. Okay, so you can see the relationship in this architecture. Okay, so since you have already and discussed that our recurrent neural network and LSTM, okay, I am not going to discuss that in detail. Okay, so since S3 or all the hidden layer information are computed using the previous hidden layer information, which contains the information related to previous inputs. So we can say that the recurrent neural network can capture the previous contextual information, and using that only we are going to predict the future words. Okay, so you can replace the recurrent neural network with LSTM or GRU, etc. Okay, so there are different variants of this LSTM and RNN. So stacked versions of RNN or LSTM are available. Bidirectional variants are available. So different variants are available. So you can use any of the variants to design the decoder model, except the bidirectional variant. Okay. So in bidirectional variant, we have two networks which captures the contextual information from the first word to the last, and from the last word to the first. Okay, but in language modeling, we don't have the concept of capturing the context from last word to the first, because if you want to do that, you should know what should be there in the end. But language modeling is basically predicting the future words. Okay, so we don't know future. Okay, so you cannot go to the future and come back to the past, okay, to generate the embedding or to generate the representation. So that is the reason we are not going to implement decoder using bidirectional variants of the RNN or LSTM. Okay, we can use the unidirectional variants of RNN or LSTM or GRU. Okay, just unidirectional variants. So based on the previous information, you can predict the future information. Okay, don't use future information to predict the future information again. Okay, so that is used in bidirectional variants. Okay, so in this case, encoder-decoder architecture or language modeling concept, you cannot use that. Okay, so this way you can finally generate the representation or design the model. Okay, so we can make a few more modifications into the network. Okay, like this. Okay, encoder side converts, and instead of just feeding the previous information, we are feeding the h0 to all the networks. Okay, so why do we do that? So if you feed H0, I mean H0 actually from this diagram you can see that H0 actually is a representation of the input image. So if you feed H0 along with the previous words, your prediction of about the next word can be a bit more accurate. Okay, so that is what research is showing. So instead of just feeding the previous information, you can just also start sharing the previous headline information and the contextual vector which represents the input data. Okay, you can combine those two things and feed that information to predict the next word. Okay, so this model can be mathematically written as probability of yt is equal to, this is the previous model I have discussed, okay, here. Okay, yt is equal to v given yt y1t minus 1 is equal to probability of yt equal to v given ht. Okay, it means that the meaning of this equation is that, so what is the probability of getting white what is the probability of getting the next word as v given the previously predicted words. Okay, so that is purely based on the previous header layer information. Okay, okay, next word, what is the probability of getting next word as the future word or v as the future word? We are relying completely on the header previous header layer information. Okay, so hitting is completely relying on this h2, okay, along with this word that is given in the equation. Okay, but in new model that I have explained in the last this model, okay, along with the this previous information, we are combining the fully connected layer output of the input image. Okay, so we are combining or we are feeding fc along with the h1 information to predict anything about the unknown data. Okay, so finally you can define ht as rnn of ht minus 1 comma yt minus 1 fc of I. So ht minus 1 is the previous header information, yt minus 1 is the previously predicted word, fc of I is the fully connected layer of the or of output of the fully connected layer at the input side. Okay, so that is going to be a vector, and you have to make sure that the dimension of ht minus 1 yt minus 1 fc of I always should be the same. Okay, so yt minus 1 can be different. Okay, okay, it can be different. So according to that, you have to change the size of ht minus 1 as well. Okay, so dimension of the vectors should be checked very carefully. Okay, so this architecture is called as encoder-decoder architecture. So this is used for image capturing problem, generating the image representation for text representation for an image. Okay, generating the description of an image. Okay, you can use this task in any domain, okay, where the input data is an image or the output data is a sequence of words. Okay, you can also apply this encoder decoder architecture, this encoder decoder architecture, or one to many encoder decoder architecture in applications like if you want to generate a if you yeah, if you want to generate some information about a signal or a speech, in all those cases you can use this model. The input is going to be a speech signal, and you can convert that speech signal into some vector representation using CNN or other algorithms. And in signal, I mean, if you want to convert a signal, normal signal, into some textual representation also, you can do that. Okay, this is encoder-decoder architecture. Now we are going to, okay, so this is how we define the entire model. So encoder is defined using CNN, and decoder is designed using ht is equal to rmn of ht minus 1 by t minus 1. Ht is equal to, okay, you can combine, I mean, there are two different implementations of this for the computation of ht. Okay, finally what we do is for predicting the output word, we can use a softmax layer. Okay, I hope you know about the softmax activation function. So softmax activation function finally will give you a probability distribution of the predicted tags. Okay, if you have 10 words to be predicted, okay, or if you are using these kind of models, and you can represent a vector as a 10-dimensional vector if you have 10 words in the vocabulary. Okay, so softmax layer will predict 10 values, which will be a part of a probability distribution. Okay, so the word with the maximum probability can be assigned as the prediction of that particular model. Okay, so this is another important application of encoder decoder architecture, machine translation. So if you feel if you want to ask any questions, okay, please feel free to ask in between. Okay, you can pause the same in the chat also. I'll look into the questions from time to time. Okay, so this is a machine translation task. So machine translation is the task of converting a text in one language to another language. So that is, you might have used the tools like Google Translate, Bingo Translate, Yahoo Trans, not Yahoo Translate, okay, Bingo and Google Translate and other tools. Okay, so basically machine translation uses two neural networks, okay, two different variants of the basic encoder-decoder architecture used for implementing machine translation uses two different variants of encoder-decoder architecture. Sorry, recurrent neural network. Okay, variants of recurrent neural network means it can be long short-term memory networks, gated recurrent unit, or stacked versions or bidirectional versions of the algorithms. Okay, here the decoder part does the same thing, like generating the uh, generating words one by one, okay, by looking into uh, the contextual data and the previously predicted data. But in the case of machine translation, the input side, you will have to do a lot of things compared to the image capturing problem, because input is going to be a text. Okay, so input is going to be a text in one language and output is going to be a text in another language. So you'll have to find a method to capture the entire semantics of the input data. Okay, in the case of image processing, we have a lot of algorithms which can perform very well to capture the relationship between to capture the relevant information from an image. But in text, it is very difficult to find such things. Okay, here in the encoder side, we are going to use in this encoder decoder architecture, we are going to use a recurrent neural network for capturing the contextual similarity between the sentence or words. In encoder side, you can use all sorts of variants of the recurrent neural network. You can use bidirectional variants, you can use stacked versions, okay, you can use unicode represent, sorry, unidirectional variants, etc. Thing is, why we are using bidirectional variant at the encoder and why we are not using bidirectional variant at the decoder. In decoder, we have to predict the future, so you cannot go to the future and come back to the present. But in decoder, the input sentence is given, you know what is the word at the end, okay, end of the sentence. So that knowledge is there. Okay, so we have the knowledge, or the machine has the knowledge about that. So it won't be a problem for the machine to go from the first word to the last and last word to the first. Sorry. So it won't be a problem at all. Okay, so here we can use any of the neural networks like RNN, LSTM, GRE, or bidirectional RNN, bidirectional LSTM, bidirectional GRE, or stacked RNN, stacked LSTM, stacked GRU. What is the meaning of stacked RNN or stacked LSTM and stacked GRU? In a basic recurrent neural network, we have only one hidden layer. So if you want to increase the number of hidden layers in a recurrent neural network, you have to increase the, or you have to stack two hidden layers, one on top of another. Okay, you cannot simply increase the hidden layers just like you increase the hidden layers in the neural network, deep neural network. Okay, that is different. Okay, so our objective here is to translate the sentence, I am happy to make coach home. Okay, so input is going to be a sequence of words and in source language, and the output is actually a sequence of words in target language. So both are represented as xt and yt, and the model, so the encoder model is ht is equal to rn of st minus 1 xt. So hidden information for one uh, time step. Okay, st means hidden information at one time step. Okay, so that can be designed using RNN network, which takes HST minus 1 and XT as the previous inputs. Okay. In the case of decoder, so decoder can be implemented in the same way as you implemented decoder in the image capturing problem. Okay. Even though the architectures are same, you cannot use the same network because depending upon the data, the network may vary. So you cannot completely rely on the network trained for that particular purpose. Okay, in this case. Okay, but the architecture wise, it's almost similar. But when you go into the deep, okay, all are different. Okay, so these are the places where we can apply encoder-decoder architecture. So one is video captioning. So it's similar to image captioning. Video captioning problems are there. Video captioning is similar to it's a hybrid of machine translation and image processing. So video captioning can be considered as a sequence of a video can be considered as a sequence of generating a sequence of words from a video is a sequence of image frames. Okay, so you can consider as a sequence of image frames, and if you want to capture anything from a sequence, you have to use algorithms like RNN, LSTM, or GRU. Okay, then a text summarization is the process of summarizing a text, okay, into one paragraph. Question answering, okay, is actually one more. Okay, dialogue management is also there, so you can combine these two applications. Okay, since the complexity of these two things are very huge, then uh, people were thought of developing these two things separately, but now we can use the same architecture for implementing question answering and dialogue management. So you can use the many-to-many encoder-decoder architecture in applications where your input is a sequence of entities and output is also a sequence of entities. Okay, so that is the problem. You can use this encoder-decoder architecture for generating a video sequence from a given set of words. Okay, then text prediction and transliteration. Text prediction means for predicting the next word given a sequence of words. Okay, there also you can use that concept. And transliteration is the process of converting a script into another script. For example, when we type or post something on the social media, we'll try to mix up different language, right? English and our native language. So in that case, to process the data, we may have to convert the scripts in our language to English language or English script or vice versa. So in that case, that process is called as transliteration. Okay, it is different from translation. Okay, so if you have any questions, please let me know. We can have a discussion in between. Okay, hope you don't have any questions. Someone is speaking. Okay. Attention mechanism is actually inspired, the concept is inspired from how we translate a sentence, okay, into another language. So when we translate some sentence or when we look into something, we or this you leave the translation concept. So when you see something, you will focus only on the object you want to see. Your focus will be, I mean, you don't focus on the background images or some other nearby objects. You'll focus only on the object you want to see. Okay, that is how we identify the objects basically. And in attention mechanism, when we translate some sentence into another language, we'll focus on some certain parts or input words, okay, to predict the correct uh, output. So attention mechanism is a concept which is used for doing that. Okay, so to predict a word, you will have to look into some other words in the source language sentence, or suppose you want to translate a sentence from English to Malayalam or English to Tamil. Okay, so if you want to generate a word in Malayalam or Tamil, you have to concentrate for focus only on that input word, which is going to be translated into the target or output. Okay, so we'll with the help of attention mechanism, we can selectively focusing on the certain part of the input data. Okay, so that is the intuition behind the implementation of attention mechanism. And here is an example for you. Input sentence or source language sentence is मैं football खेल रहा हूँ. Okay, that is in Hindi, and English translation is I am playing football. So the input vocabulary are मैं football खेल रहा हूँ, and output vocabulary are I am playing football. Okay, so we can arrange in rows and columns. Okay, in columns you can find the Hindi words, and in rows you can find the English words. So in the this is an ideal case example. Ideal case example means it you can see a table there. Okay, I is mapped to mem. Okay, so it means that to generate the word I, you have to focus only on the word I. Sorry, if you want to generate the word I, you have to focus only on the word name. You don't have to focus on any other word. Similarly, to generate am, you have to focus only on the word whom. Okay, you don't have to generate that word. Okay, then playing. So playing is actually is there are two Hindi words corresponding to playing. Okay, football. Sorry, khel raha. Okay, khel raha. So you can give some additional weights. Like if you feel that khel is has more importance than raha, then you can provide the values like 0.8, zero point 0.2. Okay, like that also possible. And football, basically football is translated from football only. So there you can follow transliteration. Okay, so that is the case. uh, so in the attention mechanism, what we are going to do, we are going to compute a probability distribution. Okay, so we'll also decide the amount of attention you have to pay to the input words to generate an output word. Okay, or output tag, whatever. Okay, so this is how we do the computation. How can we make the decoder understand the importance of source language words in generating the target language words? Okay, so what we do is, since we have these vector representation for each word, 1 0 0 0 1 and 4 zeros. Okay, so to predict I, we'll do some computation like 1 into word representation for, or hidden layer representation for main. Okay, then am into hidden layer representation for football. Sorry, am whom. Okay, so there is a mistake. Okay, then 0.5 into playing and 0.5 into, sorry, 0.5 into KL and 0.5 into Reha, because there are two terms. Summary should be, I mean, summation should be sum. Sorry, one. Okay, since it is a probability distribution. Okay, finally you are going to have a probability distribution. Okay, so 1 into HT for main. Okay, then 1 into HT for AM plus 0.5. Okay, into HT for football and sorry, playing, and 0.5. Okay, into playing, and 1 into football. Okay, so this is going to be the mathematical equation, and this is called as linear combination of the input data. Okay, now we are trying to map this linear combination into the decoder side. Okay, we are going to convert this, I mean, we are going to use it for the decoding part. Okay, so how do we compute the attention? Okay, here I told this is how attention is computed. Okay, we can identify the input positions where you have to focus so that the object will be identified properly, or the translations will be identified properly. Okay, everything depends on the data on which the model is trained. Okay, so the attention mechanism is like this. Okay, AIT, we have to compute the attention scores. AIT is equal to F attention of ST minus 1 HI. So it tells you the information like the AIT means, when you compute AIT using this equation, okay, it tells you the importance of uh, some certain tth, or yeah, ith source language word for predicting the tth target language word. Okay, how important a source language word, okay, is, that is actually going to going to be computed in this case, attention mechanism. So the function f attention is going to compute the importance of ith word in predicting the tth word. So that is the meaning of the statement AIT is, or expression AIT is equal to F attention of ST minus 1 HI, where ST minus 1 is the hidden layer information at the decoder side, and HT is the hidden layer information at the target language side, sorry, source language side, encoder side. Okay, so why we are not considering ST here? Why we are considering ST minus 1 only? So because we are focusing, we are predicting the current word. So to predict the current word, we have to rely on the previous word prediction. Okay, so that is the reason why we are focusing on ST minus 1 and HI, and both ST minus 1 and HI are should be the same size. Okay, size. Okay, that you have to consider. And finally, attention mechanism is actually, even though you can finish the computation of AIT here, okay, but we are interested in converting all this course into some probability distribution. Okay, so probability distribution equation is like this: alpha it is equal to e power ait divided by sigma I equal to 1 to t e power ait, where t is the total number of words in the vocabulary or in the data set. Okay, so this equation will give you an idea about the probability of focusing on uh, ith source language word for predicting the tth source target language word. Okay, so what is the probability of predicting ith source language, sorry, tth source target language word by using ith source language word? Okay, so that is the computation, and all the values are between 0 and 1. Okay, since it is the probability distribution. So remember the equation: alpha it is equal to e power ait divided by sigma t equal to 1 to t e power ait. Okay, so there are different ways of computing AIT, and the way you decide or design or define the alpha attention plays a major role in the performance. Okay, you can decide or define multiple ways. Okay, one way is Baudanu's attention, and another way is Luong's attention, and another way is dot product method. Dot product method is the simplest way of designing the attention mechanism. Okay, dot product means just take the dot product between the previous hillary information and uh, HI, or the contextual information. Okay, and Luong's attention is also called as general attention. Okay, actually he completed his PhD in machine translation from Stanford University. Okay, so he only first proposed this Luong's attention mechanism. Okay, that was his contribution, and later it was updated using different other methodologies. Okay. So in Luong's attention, it is also easy, but compared to dot product kernel, it is a little bit complicated. Okay, thing is AIT is equal to ST minus 1 T WHI, where ST minus 1 and HI are vectors, and W is a matrix. So you have to learn the matrix W. So in neural network, the objective of any neural network is to learn the weight and bias. Okay, so here you have to learn the optimal weight, okay, or W. So you don't require neural network also, but without using neural network also you can compute the weight. Okay, but you have to make sure that that weight is the optimal weight. Otherwise, Luong attention may fail. Okay, so here you have to consider the dimensions of st minus 1t and uh, this W. Okay, so Baudanu's attention or concat product attention is the most complex or complicated attention mechanism, okay, among these models. Okay, so attention mechanism, Baudanu's attention mechanism is defined as alpha AIT is equal to V8TT tan h of W1 ST minus 1 plus W2 HI. Okay, so here V, W1 and W2 are learners, okay, or trainable parameters. So you have to train the neural network to predict those values. Okay, so tan h, why we are using tan h here is you have to, if you want to deal with the both negative values and positive values in the data, I mean in the embeddings or word vector representation, you can use tan h value. Okay, it will help you to reduce vanishing gradient problem also. Okay, tan h actually maps anything provided to it into a range of -1 and +1. Okay, so that is the reason why tan h is used here. So here, Baudanu's attention is a proper neural network. Okay, the difference between the proper neural network and the attention mechanisms. Okay, here in attention mechanism, only Baudanu's attention is going to be used. I mean, going to use the neural network. Okay, so here in attention mechanism, even though I mean basically in all the neural networks we have some input and output. Okay, based on the errors in the output, I mean errors obtained at the output layer, we propagate the error back to the neural network, I mean input layer, to train the neural network. That process is called as backpropagation. That algorithm is called as backpropagation. And unfortunately, in encoder-decoder network, even though we have three networks, if you are using encoder-decoder network with the attention mechanism, you will be having three networks in your model. So all these models are trained simultaneously. Okay, and you cannot find a separate ground truth for encoder or this attention network, or you can also find a ground truth for or something like that for I mean, you can in decoder side you can have input and output. Okay, but in the encoder side and deep I mean attention networks, you cannot find any outputs. Okay, what you do is like every network, since everything is connected in the encoder decoder architecture. Okay, so you can pass the error obtained at the decoder side back to the input, so this encoder, okay, for training the neural network. So it is time consuming and uh, complicated because you have to consider a lot of things while training the neural network. So Bowden's attention is the most commonly used attention networks. Okay, and Luang's attentions are also be used because since if you have more data. Any question? Tulasi Krishna has raised a hand. Hello.
Ma'am, Tulasi ma'am.
Okay. Shall I continue?
Yes, sir.
So, in while designing the neural network, you have to consider this thing. Okay, Encoder doesn't have any I mean output or ground truth, and attention network also doesn't have any ground truth. So everything will be trained simultaneously. So it is a kind of end-to-end training. Uh, all the networks are trained simultaneously or together only. Okay, so the error generated at the decoder side will be propagated back to the input encoder, and then all the weights and biases will be updated accordingly. Okay, so this Berthenus attention we use everywhere, and Luong attention is also used in many places. But even though dot product kernel is sorry, dot product attention is the simplest way of designing the attention mechanism, we don't use it. The reason is if you implement a encoder-decoder architecture for applications like machine translation or text summarization or question answering, uh, you have to use a huge amount of data, and otherwise you will be having a pre-trained model for to start with. So in that case, you the neural network based methods will give you a better performance because neural networks can learn much more important or relevant or significant features or information from the data than the dot product methods or human engineered methods. Okay, so basically we use Bauden's attention or Luong's attention. Sometimes you can see the term concat product attention and general attention. Okay, so this is all about the theory part of the attention mechanism and encoder-decoder architecture. Okay, then now I think we can go for the hands-on session. So if you have any questions related to this attention mechanism and encoder-decoder architecture, please let me know. And understand that I mean, 1 hour is not sufficient enough to explain the real concept behind the encoder-decoder architecture. So still, this is the essence of an encoder-decoder architecture with the attention mechanism. So when you implement the encoder-decoder architecture, you have to make sure that the output is going to be a sequence of words. Input can be either a sequence of words or an image or a video, something like that. Okay, so in that, or you can output has to be a sequence. Okay, that is the only condition. Sequence means it can be a sequence of image frames. Okay, it can be a video. Okay, that is the only requirement we have to use. We should have before applying the encoder decoder architecture, one to many or many to many. Okay, so I'll be taking the example of machine translation to explain the attention mechanism with encoder decoder architecture for in the hands-on session. So if you want, we can take a 5 minutes break. Okay, then we can continue the session. And in between, I can take a few questions related to this topic. So please feel free to ask questions.
Participants, if you have any doubt, please ask.
Okay, then we can continue with the hands-on. So I'll be using Google Collaboratory for doing the experiments. So hope you can see my screen. Okay,
Yes, sir.
okay, thank you. So I am using there are different frameworks for implementing deep learning algorithms. TensorFlow is one framework, and you can find other frameworks like PyTorch, Caffe, Keras, etc. So here Keras is a wrapper for TensorFlow. CNTK is another framework. Okay, you can find a lot of frameworks, and Piano is another one. Okay, I am using a Keras based, so TensorFlow based Keras for implementing the network for machine translation, and Matplotlib for plotting something, and train test split available in sklearn. So sklearn is a Python package which can be used to implement all sorts of machine learning models. Okay, you can also find a lot of functions related to pre-processing the data and other activities. Okay, then Unicode data for dealing with the Unicode information. RE for regular expression. I don't know whether I am using that. NumPy is a numerical Python. Okay, for all the linear algebra operations, you have to install NumPy in your laptop. Okay, then OS for changing the directory and finding the path. Okay, then IO for dealing with input output data, and time. Okay, is for computing the or understanding the time required to process each operation. Okay, so I am using Spanish to English translation data. So you can download the data from this website. Okay. Finally, unzip. All the data will be displayed. So when you call cat spa.txt, it will give you the sentences in English and corresponding translations in Spanish. Okay, my hobby is playing golf. Okay, so corresponding Spanish sentence you can find. So this is how we prepare data for a machine translation task. Okay, bilingual corpus or bilingual data set is required. So in one column you can keep the source language sentences, and in other column you can keep the target language sentences. So our final objective is to find a map between the input or source language words into target language words. So this is just printing the contents in the file spa.txt that is going to be used for dealing with this task. Yes. Okay. So in natural language processing, in almost all the AI tasks, the first and foremost thing you have to do is a pre-processing. So pre-processing, the steps involved in pre-processing the data may vary from application to application. You can decide what are the pre-processing steps you have to follow for implementing an application. So here what we are going to do is we just convert everything into lowercase and strip off all the new line characters at the end. Okay, so strip function in Python will basically removes all the new line characters which occurs at the end of a sentence, and lower casing function will convert everything into, or lower function converts everything into, every character into lowercase. And in most of the machine translation tasks, we append two keywords start and end to mark the beginning and end of the input data. Okay, so start and end. So this is the pre-processing step we have followed in this code. You can use, if you want, you can use other models also. Okay, so other methods also, pre-process sentence. So now we'll see how it goes. I mean, how it works. English sentence is equal to I go home right after work. So print the pre-processed sentence, en sentence. Okay, when you pass this thing, okay, you can see that everything has become small letters, and at the end and beginning you have two keywords. Okay, start, end. Okay, similar to that. Okay, when you pass the Spanish language into the uh, pre-processed sentence function, okay, you will get everything. So here also V is a capital letter, so V will be as a small letter. Okay, so everything is similar to the previous thing. Okay, so this is the importance of pre-processing. You can do some other use some other pre-processing task also, but you can find the pre-processing task like stop word removal. Okay, stop word removal is nothing but the removal of the frequently occurring words in the language. But in machine translation, question answering, and text summarization and sentiment analysis kind of task, we don't do that. In sentiment analysis, we can remove the stop words, but you can remove a limited amount of stop words, because you cannot remove the words which are negation words. Okay, no, not, never, etc. cannot be removed from the data. But in the case of machine learning translation and other I mean, similar applications, we cannot remove the stop words because each and every word are important. Okay, so now what we do, we create the dataset, or after pre-processing we prepare the dataset required for training the neural network. So def create dataset is doing the same thing. Okay, we are going to keep n number of words or n number of sentences. Okay, so that is actually to reduce the complexity of the algorithm. You can, if you want, you can keep n number of sentences from the corpus. Okay, n number of English and corresponding translations in the Spanish. Okay, so lines is equal to, you can see the in the fifth line, lines is equal to io dot open path encoding is equal to UTF-8 read strip dot split. Okay, so if split function, okay, actually converts everything into different sentences. Wherever you find a new line character, the split function will split the data from that point. Okay, then strip off, okay, all the things, unwanted things will be stripped off, and that data will be read as a UTF-8 data. Okay, so providing a path, the algorithm will be able to go there and check for the required information and get it. Okay, so that is the line meaning of the line lines is equal to io dot open. Okay, now we are creating a word pair. So, okay, word pair is like process the sentence for w in l dot split or l in lines uh, of 0 to or whatever, nothing to number of examples. So word pair is going to be, okay, so pre-process sentence. Okay, uh, it actually separates a sentence into different word pairs. Okay, so path to the file is spa english slash spa.txt. Spa english is the folder name, and spa english is the data. Sorry, spa txt is the data. So we'll create separate data for en and sp using the create dataset, and we provide the path to file, and we will tell that we are going to keep only the first 30,000 or 3,000 sentences. Okay, so finally when you prepare the length, okay, you can I mean, when you prepare the contents, you can see this is how the output output of this create dataset looks like. You can also see the vocabulary size here. Okay, it has to be 3001. Okay, so we have prepared as Spanish data. Okay, sorry, yeah, Spanish data and English data, which can be used for training the neural network directly. Okay, so in many of the NLP tasks, the first thing you have to do is after pre-processing. So it is a part of pre-processing only. The first thing you have to do is a task called tokenization. Tokenization is the process of converting a text into tokens. A token can be a word or a punctuations. So there are different functions for converting a sentence into tokens. Okay, if you are implementing a sentiment analysis task or something like that, you can use the tokenization function available in the NLTK, Natural Language Toolkit library, word tokenized function is there. Or if you are developing a deep learning model, you can use the tokenization function available in the frameworks like Keras. Okay, so tokenizer has to be defined. Okay, lang tokenizer is equal to tf.keras.preprocessing.text.tokenizer. Okay, so we are going to split a sentence based on the splitting criteria is space. Okay, we are not going to use any filter or splitting criteria. So basically, we will tokenize a sentence into one word. Okay, so lang tokenizer is equal to tf.keras.preprocessing.text.tokenizer is the function called. Okay, so instead of calling that function frequently, you can use the handle to that function, which is called as lang tokenizer. So once you define the function, you can simply apply the function onto the uh, data. Okay, so data you have to provide here lang. Okay, lang tokenizer dot fit on text lang. So fit on text is a method or function available in TensorFlow to apply the uh, any question. Okay, okay. So fit on text is a function which is used to uh, actually all the fit functions are used for training something. Okay, in Python you can see that if you implement a model, you'll be using some fit function. So fit on text function is basically used for applying the tokenizer onto the data. Okay, then what you do next? Tensor is equal to lang tokenizer dot text to sequences of lang. Okay, so after converting the input data, we are going to convert the text sequence, okay, or text data or words into corresponding indices. So after okay, so corresponding indices means we'll create a vocabulary or a dictionary which contains a word and corresponding some index value. So as we all know, computers cannot understand the text. We have to convert the words into some vectorial representation. So text sequences actually helps you to convert or replace words with the corresponding index value in the dictionary. So actually it doesn't have any meaning. Okay, so you may be wondering why we are using index value. Okay, we can sort the words alphabetically and we can provide the index value 0 to the first word, 1 to the second word, 3 to the next word, okay, and so on. Okay, so what is the point in converting the data or words into some integer values using this function? So we will see that later. Okay, so once you convert the text into a sequence of integer indices, what you have to do is we had to pad the sequence with some zeros. The reason is in many cases you cannot expect the input sentence to be to have equal number of words. Some sentence may have 5 words, some sentence may have 10 words, some will have 1 word. Okay, you can have different number of word length, okay, sentences. Okay, so to make the sentence length equal, so you have to understand that all the machine learning or deep learning model should or can deal with a matrix, input matrix only. So in a matrix, all the number of values in each row and columns are going to be the same. Okay, so to make a matrix of such kind, we have to pad some zeros. So padding can be done in two ways: pre-padding or post-padding. Okay, pre-padding means appending zeros at the beginning of the input data. Okay, so that kind of application is called pre-padding. And if you want to append zeros at the end of the input data, then you can call it as a post padding. Okay, so this will return the language tokenizer and tensor. So tensor can be used for further processing. Okay, now what we do, we load the data set. Okay, we have to provide the path and num examples is equal to none. Okay, target language input language is equal to create data set of path comma num samples. Okay, create data set means it will go to this function and it will take that many examples from the data and prepare the data. If you put num samples is equal to uh, where is that? Okay, some value, like here it is 3000. Okay, then that many sentences from the input data will be taken for the analysis. Okay, so once you get the target language and input language, you'll have to convert that into tensors. Okay, tensor is nothing but a three-dimensional matrix. Okay, two-dimensional matrix is matrix, and if it is a three-dimensional, then we can call it as a tensor. Okay, so for getting tensor and input language tokenizer, we can call the tokenize function, and for generating target language tensor and target language tokenizer, we can use this tensor target language tensor. Okay, or target language tokenize function. So here, in this case, we fix the total number of examples as 3000. It means that we will take the first 3000 sentences from the input data. So input tensor, target tensor, input language, and target language is equal to data set, positive file, number of examples. So we'll have to, based on the split, I mean, okay, where it is, yeah, load data set. Yeah, based on split and number of examples value, we can decide the matrix. Okay, we can decide where I am. Yeah, input tensor, target tensor, input lang, target language is equal to load data set. Okay, so here we are creating the input data and output data. So we are going to use this input data and output data for further processing. Okay, so here you can find that max length target and max length input is equal to target language target tensor shape, input tensor shape. Okay, so those are the functions. You will get the length. Okay, how many parameters, how many values are there in your tensor. Okay, that is going to, I mean, that is the output you are having after running this code. Okay. So what we do next, once you prepare the data, we have to, in most of the cases, we won't be having a separate training data, testing data, and validation data. So you have to prepare these values, okay, with the help of train test split. So when you perform that operation, okay, so you have to make sure that translation data and yeah, okay. Sorry, training data and sorry, validation data and test data should be coming from the same distribution, and training data can be a separate distribution. So if you want to divide the data into train data, test data, and validation data, you can divide the data into train data and some other data, and that data can be divided further into validation data and test data. So the validation data should always come from the uh, I mean, it should be a part of the test data. I mean, uh, both should have the same kind of distribution. Okay. So here we can have some output size. Okay, len of input tensor train, len of target tensor train, etc. So what we do next, we'll convert. I mean, we are representing something like this. Okay, you can find output here. These are indices and corresponding words. Okay, I am hungry, that and you can find the Spanish translation also. Okay, now we are going to define the hyperparameters of the neural network. So for a neural network, we have hyperparameters and parameters. Hyperparameters are learned by, I mean, are assigned by the human beings or the engineers, and the parameters are learned by the network itself. Okay, so here buffer size, batch size, steps per epoch, embedded dimension. So embedded dimension is very important because embedded dimension is equal to 256. So all the words will be converted into a 256 dimensional vector. Okay, that is the meaning of embedded dimension. Un is equal to 1024. It means that if you are using uh, uh, unidirectional LSTM or RNA or something like that, then you can have 1024 hidden layer neurons in the network, and vocab input size, vocab target size, etc. There, then data set is equal to tf dot data set dot from tensor slices. Okay, so we can, if you have a multiple data set, okay, then you can use that function. Okay, then so data set is equal to data set dot batch. Okay, so we are going to make prepare the data in batch wise also for further analysis. Okay, it is too difficult to train the entire network by providing the entire data. Okay, so now these things are not that important. Now we are interested in the definition of the encoder network. So as I said, encoder networks can be implemented with any variant of RNN. It can be unidirectional, bidirectional, stack, or anything. Okay. So here what we are going to do is we are going to define the neural network using GRU, gated recurrent unit. Okay. So batch size and encoder units are there, then embedding dimension is going to be, so these two sentences are going to be the actual model definition. Embedded dimension is equal to TensorFlow keras, layers, embedding, vocab size, and embedding size. So vocab size means no total number of words, and embedding size means the size given by okay the size to which the words are converted. Okay, so embedding layer will always be there in the deep neural network if you are dealing with the image kind of data. Okay, but an embedding layer is basically used for converting an index into a number or a vector, so that index can be created only by only for text related data. Okay, so those two highlighted sentences, self.embedding and self.gru, as the two steps involved in the definition of encoder network. You can replace GRU with LSTM or simple RNN, or you can replace the entire thing with some conventional machine learning classifier, okay, instead of GRU, and the features extracted from other models. Okay, then def call function is there. So if x is equal to self dot embedding, output state is equal to self dot gru of x comma initial state. Okay, return output and dense. Okay, so actually it is for predicting the output of the input data. Okay, and initialize hidden state self. Okay, so that is also very important, because initial values are very important in machine learning applications, especially in deep learning. If your input data is too wrong, okay, so if your uh, input information is like uh, the variance or difference, or it is, if it is not at all related, then it is too difficult to train the model. Okay, so initial values are very important. Initial hidden, sorry, initial, actually it is initial hidden state. Okay, basically in recurrent neural network we consider the initial previous hidden information as zero vector, but if you want you can consider, but that is by intuition, because before the first hidden layer or first time step we don't have any other information. Okay, that's the reason why we are putting zero vector as the initial hidden state for the recurrent neural network. Okay, but you can also use some other information, but that should be chosen very wisely. Basically we don't consider any other vectors for initializing the hidden state, first hidden state. Okay, so finally we are going to call the encoder function. Encoder is equal to encoder of vocab input size, embedding dimension, units, batch size. So batch size means these many sentences will be given for training in a go. Okay, vocab input size means total number of words you are going to feed. Embedded dimension means the dimension onto which the words are converted, and units means number of hidden layer units. Okay, then sample hidden is computed as encoder dot initialize hidden state. So this is the first hidden state information, and sample output comma sample hidden layer is equal to encoder of example input batch comma sample hidden. So for the next hidden layer information, we can use the previous hidden layer information and input batch. Okay, so you can start from the first batch or second batch or something like that. Okay, that you can decide. Okay, so that is happening here. And one more thing is that if you want you can yeah, in GR you can say that return sequences is equal to true and return state is equal to true. So return state is equal to true means you have to return the state information. State information means the memory information you compute, or the model computes, or the network computes during the training. Okay, so that is required for many of the processing. Okay, especially if you are dealing with the bidirectional versions, then you may require that kind of additional information. And return sequence is equal to true means if you are using stacked versions of the RNN or LSTM, okay, you have to uh, share the stacked versions are basically used for improving the or increasing the number of hidden layers in a network. So in that case, you have to share the information you computed in one layer to another layer. Okay. So if you put return sequence equal to true only, it can happen. Otherwise, both networks will train something else. Okay, that the prediction won't be that good. Okay, so in this encoder network, okay, we are actually calling the functions defined for encoder network, and we can use it. Okay, for okay, now comes the Bernoulli's attention. You can define the attention network in your own way. So very simple implementation only. So here we are using Bernoulli attention. Bernoulli attention is a neural network attention. Okay, def init, super Bernoulli attention self. Okay, that you, I mean, that is object-oriented programming concept. Okay, so here we can compare the equation with the uh, original, I mean, implementation with the theory equation. Okay, here AIT is equal to VATT transpose tan h W1 ST minus 1 plus W2 HI. So here we require two weights W1 and W2. So we are defining W1 W2 as two dense layers. Okay, dense layers means fully connected layers. Okay, now we are also defining the V. Okay, tf dot keras dot keras dot layers dot dense of one. Dense of one means you are going to compute only one data. Okay, so if there are n data, you will compute n such information. Okay, then call function, what it does is, okay, query with the time axis to tf dot expand dimensions. Okay, so it means that along the x-axis or y-axis you can expand the dimensions. Okay, that is the reason why we are calling the function expand dimensions. Then attention score is equal to, so you can compare the score equation self dot v into tf dot nn dot tan h of self dot w1 of query with the time axis plus self dot w2 of values. Okay, so self dot w1, okay, w1 of query with the time axis. Okay, then self dot w2, okay, this one, and values, and just this one. Okay, then attention weights is equal to tf dot nn dot softmax of score comma axis 1, along which axis you have to compute. So that is happening here. Alpha is equal to exp ait, okay, divided by summation over I equal to 1 to t exp ait. So that is going to happen here. Okay, we will take the softmax over the entire score function. Okay, so for each score you can compute uh, the softmax information. Okay, so context vector is going to be the linear combination of attention weights and values. Okay, so we can consider this way. Okay, 1 into some vector plus 0 into some vector plus 0 into another vector plus 0 into another vector, and okay, 0.5 into one vector plus 0.5 into another vector. Okay, so this is what is happening here. Attention context vector is equal to attention weights into values. Okay, then we are defining the context vector as a tf dot reduce some context vector comma axis. So it is actually for optimization purpose. Okay, training the neural network, we are reducing the sum. Okay, so it is written by context vector as well as it will return both context vector and attention weights. Okay, so we can call attention layer is equal to attention Bernoulli attention of 10. It means that so here units. Okay, so we have to provide the number of units. Units means number of layer information. Okay, we can have n number of hidden layer information. Okay, for the training of the model only, I kept it as 10, very simple value, small value. Okay, so attention result, attention base is equal to action layer, attention layer of sample hidden comma sample output. Okay, so here we can see the attentions you obtained. Okay, in this network. So we have computed encoder network and Baudel's attention network. Now we have to design the decoder network, and we have to combine all these things for the prediction. So decoder network contains vocab size, embedded dimension, D's units, batch SC. We can define all those values, embedding layer and GRU, etc. And fully controlled networks are there. Okay, so self attention is equal to Baudel's attention, so you can use the same attention. Okay, so attention result is equal to attention weight is equal to attention layer of sample hidden comma sample output. Okay, so attention weights will be displayed, attention results are required. Okay, then attention weight may remain the same. Okay, so that is actually attention result is the one on which you have to concentrate more, because that is going to be used, okay, uh, for other analysis. But you can also compute attention weights. Okay, in some other cases you can use the attention weights as well. Okay, so in the decoder side, what we are doing is just like the previous implementation. You can simply initialize all those things. Okay, self attention is equal to version attention, self dot decimal units. Okay, uh, so where is, yeah, so it is actually printing some numbers. Okay, integer values. Okay, then we'll define the call function. So this is decoder, yeah. Context vector is equal to attention weights is equal to self attention comma, sorry, at self attention of hidden comma uh, enc output. I think it is encoder output. Okay, so you will get the context information at this context vector. Okay, then we call the embedding layer, we create the text data and call the embedding layer. So here you can find the equation. So you can call the embedding layer. Basically what it does is it will convert the indices. Now previously I was talking about the indices. So these indices can be converted into vector representation by a lot of comparison. Okay, or you can automate it. Okay, so embedding layer does that in conversion of the input index into a vector. Okay, that is the task of embedding layer. So after that we can do tf.concat, tf.expand the dimensions, context vector comma I j, sorry, 1 x is equal to 1. So context vector, context vector and x will be combined together. Okay, for concatenate for generating the target language words. Okay, output state is equal to self dot guru, gru x, gru contain what are the informations there in the gru. So we haven't used the gru. Okay, so that's the reason gru output is not there. Okay, so we can compute the attention layer and just predict. Okay, then decoder can be converted as a decoder of vocab tree, vocab tar size, embedded dimension units, batch size. So it means that it is searching for some uh, something. Okay, and sample decoder output. I mean this underscore. No, it can take any value in Python. Okay, so decoder of tf dot random dot uniform. So everything will be in the random initial random format. Okay, everything is in random format. Okay, it comes from sample decoder output comes from initially it comes from uniform distribution, and you can make it normal distribution also. So there are different choices you can make while tuning the model. Okay, then finally once you define the model, you can define for the define the other important aspects like optimizer, loss function, etc. Sorry, uh, bias function, etc. Okay, so loss function only. Okay, optimizer, here you can find a lot of optimizer. All the optimizers are variant of an algorithm called a gradient descent. So here you can use ADAM or ADA delta, ADA grad, stochastic gradient, RMS crop, etc. are the examples of different optimization algorithms. You can choose any of the algorithms, because there is no rule that you have to follow this particular algorithm only, because everything is data dependent. Okay, you cannot choose a particular optimization algorithm or similar kind of hyperparameters for training a model. Okay, so similarly we have different loss functions also. So how do you define the loss? Okay, loss between the input data and the original or predicted data, and not input, predicted data and the original data. Okay, so there are a lot of loss functions like categorical cross entropy, sparse categorical cross entropy, binary cross entropy, etc., or absolute mean square or like that. Okay, you can find a lot of uh, optimization functions in the Keras library. Okay, here what it is, sample output. Okay, so you can print those things, and here Keras. Okay, production is equal none. Okay, so loss function can be defined this way. Okay, mask is equal to, so you can use your own mask function, otherwise you can use the predefined, okay, or user defined loss functions instead of predefined loss functions. Okay, in user defined loss functions, def loss function of real pred. Okay, uh, we can create a masked representation. Okay, mask is equal to tf dot mask dot logical not. Okay, tf dot mask dot equal of real comma 0. Okay, then so it is actually creating a zero matrix. Okay, or a sparse matrix. Okay, finally loss underscore star equal to mask. Okay, so that is one way of defining the loss function. So this is the training phase. Okay, so actually this is the implementation of the gradient descent algorithm. Okay, so gradient descent algorithm is actually basically it does the updation of the weights and biases in the neural network. Okay, so here you can find the updation of the loss. Okay, loss will be updated here, and variables gradient, you are computing the gradient. Okay, gradient means first derivative, then you are applying the optimizer, and you can compute the update the batch loss. Okay, then once you do that, define the optimizer and the loss function. Okay, then we can define the epochs. Epochs means when you start from the input data, go to the output data, sorry, starting from the input layer, go to the output layer, compute the prediction, take the error between the prediction and the true label, propagate that error back to the input layer, so that you can find or you can update the weight and biases, which is the major reason behind the error between the predicted data and the original data. So we have to update our vocabulary. Okay, or you have to uh, keep on updating these training epochs. Okay, that process is called as epochs. Okay, so that process is called as one epoch, and you can train the neural network for multiple epochs. Okay, so epochs, we don't know. I mean, generally we don't know after which epoch we have to stop the training, but now we have concepts like early stopping in TensorFlow Keras for stopping the training after a certain number of epochs if the loss functions are not getting updated, or if the uh, uh, loss is converges to a value, or if the loss becomes zero, then we can stop the training. So that can be automated. Okay, then encoder hidden layer. So we'll initialize the encoder hidden layer. Okay, then total loss is initialized as zero. So in training a neural network, what happens if you have 1 lakh data in the input data, or 1 lakh data points in the input data? So you have to compute the loss for each and every data point, and finally we'll take the average or sum of the whole data. So that uh, error, average error, or sum of the error is going to be minimized. Okay, that should be remembered. So we don't do simultaneously all the process. We'll do it separately, and we'll take the average or sum. Okay. So batch loss, total loss. Okay, that is very basic thing. Okay, so this is all about the encoder decoder architecture with the attention mechanism. So you try to, instead of Bernoulli's attention, you can try to write your own equation for general attention or Luong's attention and dot product attention. Okay, so Luong attention is very simple to write. So, okay, AIT is equal to ST minus 1T WHI. Okay, let's try it once. I think so. We don't require two weights. Okay, one weight is enough. Okay, then we don't require V also. That can also be commended. And so this here, it is going to be 4 equals self dot t minus 1. Okay, self dot, I think we have to np dot mat mul. Remember the equation for matrix multiplication in uh, TensorFlow. Np dot mat mul and st minus 1. There also you can do that. It is dot product. Okay, st minus 1 trans. Okay, it is not that dot transpose. Okay, you can take the dot product between those two things. Okay, so it can be easily done. Basically, you can do this self dot values where we have defined the values. Okay, values do that we can self dot values. Okay, np dot mat mul of self dot values comma, okay, self dot w1 of what hi. Okay, this is values. Okay, this has to be free with time axis. Okay, this way you can define the general attention mechanism. Okay, so you can replace np.matmul with the function available in the TensorFlow for matrix multiplication. I don't remember the exact name. Okay, so you can define this in your own attention mechanism. Okay, dot product we don't use because it is very simple to implement and it is not that I mean, the performance also very low compared to other methods. Okay, so this is all about today's session, and if you want to ask any questions, please feel free to ask, or suggestions, anything. Namita madam, timing is okay, right?
Okay, sir.
Yeah.
Sir, actually, are we going to wind up the session?
Yeah, I can. If you want more discussions, we can continue. No problem.
Participants, if you have any doubt, please ask.
Okay. I think. Okay. The concept of attention mechanism is going to be the basis of the transformer networks, which will be discussed tomorrow session. So
Okay.
there are that is the latest trend in natural language processing, because nowadays, all not just in NLP, but in almost all other fields like in image processing and speech processing, you can find the applications of transformer networks. Okay, so basically, the transformer is designed for natural language processing and machine translation. Now it is being used in other domains as well. So almost all the applications, we are going to use transformer for implementing the state of the art models. Okay, that actually transformer is the state of the art in everywhere, not just the. Okay, actually LSTM, RMN, all are actually dead. Okay, because of this transformer networks. So tomorrow we will see the transformer and the BERT algorithm, and we will see some hands-on sessions on generating the embeddings using BERT algorithm. Okay, if you don't have any other questions, I think shall we wind up, madam?
Okay, sir. Thank you so much, sir, for such an informative session.
Okay, thank you, ma'am.
Thank you so much. And tomorrow we have our session and start from 9:30 onwards. And we have our second session. This is and will be a hands-on session for learning word embedding algorithm. So thank you so much, all participants.
Thank you, ma'am.
Thank you, sir.
Can I leave?
Yes, sir. Of course.
Okay.